In this video, I will show you how to write flash memory across different STM32 series U5, H7, G4, L4, F4 and F1. The core process is the same, but there are some small differences. This might save you hours of debugging. But listen, if this isn't the exact problem you are solving right now, comment below and tell me what you need, and I'll make one of the next videos on your topic. I'll explain the process using these 6 chips, so you can easily see the differences in the STM32 HAL libraries between them. You'll know exactly what to look for to make it work on any STM32 model. The first thing to look is the flash memory size. You can find it in 2 places in the datasheet: the futures and the peripheral counts table and the ordering information table. Once you know the flash size, you can write a small test program to the beginning of the flash memory. This program will write some test data to the second half of the flash. Then you can easily check if you can read the correct data back. Once you learn how to read and write flash memory, you can do all kinds of things, like firmware upgrades, storing device settings, and saving other data. Before you can write to flash memory, it must first be erased. For clarity, in this demo, you will erase the entire second half without considering the amount of data to be written. You just need to ensure that the test program residing in the first half of the flash memory is not erased. The first chip to try is the STM32 U5. I chose the U5 and not some older basic series to show that it's actually pretty simple on any series. This will help you to become more confident and choose any STM32 you need without hesitation, so you don't get stuck with something like STM32 F103 forever. That's why the F103 is at the end of this list. The STM32 U5 features a dual-bank flash memory architecture. You can ignore this naming and only look it up if you truly need an additional features it provides. For now, it's simply flash memory. To erase its second half, you must perform an erase operation on flash bank 2. Each flash bank consists of 64 smaller erase units called pages. To erase the second half of the flash memory, you will need to erase all 64 pages, starting from 0 page of flash bank 2. After flash memory is erased, you are ready to write. The STM32 U5 minimum write block is 16 bytes. All you need to do is pass the target flash address and your 16-byte array to the relevant HAL flash write function. And I think you're smart enough to figure out on your own what the flash lock and unlock functions do in this code. Reading from flash memory does not require any special HAL functions. You can simply use standard pointer operations to access the data, the same way you work with embedded RAM. The flash memory address itself is easy to understand if you look it up in the datasheet and have a basic understanding of the hexadecimal numbers. Now I want you to stop and learn one trick that makes your flash routines far more portable and easy to understand. Each MCU has its own minimum write block size, some as small as 1 byte and some up to 32 bytes. The trick is to always use maximum block of 32 bytes for all series. By always writing in 32-byte blocks, you enforce one standard: eliminate conditional code, and keep the same high-level routines running on every STM32 chip. So next time you implement flash write routines, just write 32 bytes regardless of the actual minimum block size. On the STM32U5, for example, you do this by calling the flash program routine a second time to write the additional 16 bytes. If the actual data is smaller, you can always pad the rest by zeros. Note that this doesn't affect reading at all. You can read any amount starting from 1 byte. Let's do the same erase, write and read operations on STM32H7 series microcontroller so you can see the difference for yourself. For this STM32H7, things are almost the same. Set the starting erase sector to 8 and the erase count to 8 as well. You may have noticed that the erase blocks are now called sectors instead of pages. And there's a new parameter called voltage range. But the most confusing part is that sector is counted from the beginning of the entire flash memory, not from the beginning of the flash bank 2. For this chip you can write 32 bytes in one operation, so you don't need to call the flash programming routine a second time. It's easy to get confused about this, but there's no deeper meaning behind it. Different STM32 series simply have different write block sizes, and the HAL library was built to expose those differences instead of making the behavior universal across all series. On the STM32U5, writing 32 bytes required two 16-byte write operations. On the H7, you can do it in one go. There is no deep meaning behind it, and it's not something you need to memorize. You can write your high-level flash code once and forget it along with quad word and flash word constants. And the second major difference is in how pages and sectors are counted. Page numbers are relative to the bank, while sector number is absolute. That's why for the H7 chip you set the erase sector to 8, even though it's at the beginning of bank 2. Intuitively, the number should be 0, but in reality the correct value is 8. Reading from flash memory is the same across series. You just need to use the correct flash address for the data you want to access. The next chip is from the G4 series. To avoid getting stuck with this one, note that the HAL flash program function for the G4 chip expects the actual data value, not a memory address as it did for the H7 and U5 series. The flash erase operation for the G series is very similar to the U5 series. You start erasing at page 128, which is page 0 of bank 2, and you erase 128 pages. Pages are numbered relative to the beginning of the flash bank, and this chip has additional D-bank configuration bit that enables a different flash memory mapping. But to be honest, ignore it for now. There is no need to remember this or analyze it if you don't need this feature. Since the minimum write block size is 8 bytes, you need to call this function 4 times to write 32 bytes of data. The HAL flash program function expects you to provide the actual 64-bit data value, not a memory address. In this example, you use pointer operators to cast your byte array into a 64-bit unsigned integers. Don't be confused by the syntax. It may look like a pointer, but after the cast, you dereference it to get the 64-bit integer value. and then you can read this value back by accessing the data at the beginning of the second bank. You can see that the flash erase and write operations are almost identical. The only differences lie in the minimum write block size, the sector numbering, and the fact that the HAL library for the G4 series expects the actual data instead of a pointer. The fourth chip you'll learn about today is from the low-power L4 series. Its flash memory is very similar to the G series, as it's also page-based, not sector-based. The only difference from the previous example is that you need to update the number of pages to be raised to 256, because this chip has more flash pages. Then you write 32 bytes in 4 steps at the beginning of Flash Bank 2. You just need to make sure that the write address is actually points to the start of Bank 2. This address is not the same as on the STM32 G4 series, and in this example you can see that the value uses 8 instead of 4. Reading flash memory works exactly the same as before. You just read from the flash address where your data was written. Before you forget the differences, let's look once more at the first 4 series. The first confusion comes from the fact that H7 HAL library expects the sector number to be absolute, counted from the beginning of the flash memory and not from the bank 2. That's why the H7 example sets the start erase index to 8 instead of 0. And the second confusing difference is that the G4 and L4 write functions expect actual data instead of pointers. You also have different write block sizes and write a different address. So the differences are only in erasing and writing. The reading is simple and works the same way on all series. If you are still watching this, congratulations! The hard part is done. Only 2 series are left, so let's look into the F407 first. This chip has a slightly strange flash layout with different sector sizes, but everything else works exactly the same as on the previous chips. The F407 VET6 chip has 512 kilobytes of flash memory divided into 8 sectors. To erase half of it, you can erase the last 2 sectors, which gives you exactly 256 kilobytes. You start the erase at sector 6 and set the erase count to 2 sectors. After the erase is finished, you can write new data into these 2 sectors. Now, if you modified the previous example with the correct address and tested it, you'll see that nothing gets written to memory. To fix this, just use word writes instead of double word. And if you are wondering why, you can always dig into the VPP remarks in the datasheet and the HAL source code, but only if you really need to. Word writes use 4 bytes instead of 8, so the code becomes a bit heavier. For your convenience, no loops are used here. You can see how each flash address is set line by line. And reading the flash memory is done exactly as before. You just need to set the correct address. You can see there was nothing complex with the previous chip except for the bogus VPP limitation. That limitation prevents the use of double word writes, and it's surprisingly hard to find in the datasheet. Now you are ready to learn the flash erase and write routines for the most basic and probably most popular STM32 series, the legendary F103. Unlike all previous chips, the F103 HAL libraries expect you to provide a page address for the erase function, not a sector number and not a page number. And the number of page to erase is still a regular number. This chip only supports 2-byte writes. This means our previous approach to write 32 bytes extends to 16 separate calls to the HexFlash program function. And reading is straightforward. Just use whatever approach you like, as long as you point it to the correct flash address. If you still can't figure out how to write flash memory and need some help with the source code, subscribe for the part 2 and leave a comment. That way I can help you solve every STM32 issue you're facing.